Welcome back. We're going to continue our discussion on a newer topic related to bonding, okay, and a host of other materials that are related to bonding. But before we do that, let's summarize what we learned in the previous material, okay? Now, I have repeatedly said, and I will probably repeatedly say that throughout the next unit, because you have to get this idea into you. Otherwise, it would always seem very alienated principle, okay? Metals make cations. It doesn't matter whether it's an alkali metal, alkaline earth metal, transition metal, or inner transition metals. They all make cations. Okay, I don't know of a metal yet that is negatively charged, but if you know, please do help me out with that. And non-metals make anions, that is negatively charged. Okay. Positive charge in chemistry means you lose something, and negatively charged means gain something. Okay. In a real world perspective, it's quite different. When you lose money, it's it impacts it negatively on your bank account, and if you gain money, it adds money to your bank account. And that's not how chemistry works. Positively charged in chemistry means losing electrons. Negatively charged means gain electrons. Okay. Now, I did say that in the last of the last video where I gave you some practice problems to work. Okay. Valence electrons for metals corresponds to the Roman numeral on top of the column. Okay. For example, what do I mean by, I said the sheer purpose of actually understanding what valence electrons are. Actually, I'm going to put the second one so I know the space. Right? For instance, I say sodium is under column 1A. Okay. What does that mean is sodium has only one valence electron available for bonding, and sodium is a metal, so it'll make Na1+. Okay. What is 1? Means it's a metal. It can lose the one electron it's got, valence electron it's got, and because it's lost, it's plus. Calcium is under 2A. So it can lose both the valence electrons. Now, pay attention here. Alkali and alkaline earth metals, okay, they don't have a restriction saying I would lose 1 or I would lose 2. They always lose the maximum, okay? That is sodium, lithium, potassium, they're all alkali metals. They lose all of the valence 1 electron available. Similarly, alkaline earth metals, they lose all of the 2 that they've got under 2A, so 2+. Now, on the other hand, transition metals, for instance, say chromium, okay, it's got 6B. While it's got 6 electrons, it doesn't have to do so. This is a transition metal. Okay. While it's got 6 electrons, it doesn't have to lose all 6. It can lose 3. It has the option of losing only 3 valence electrons to bond, or all 6. Okay. Which is why you would see when I name compounds, alkali and alkaline earth metals fall under one set of rules, and transition metals fall under separate set of rules. Now, you might be wondering, how am I supposed to know whether it loses 3 or 6? Do not worry. If I give you a name and I ask you to write a formulae, the name will contain indication on whether you're losing 3 or 6. But that's for a separate video. But I want you to point out the purpose of valence electron is, these are alkali and alkaline earth. This is a transition metal. Alkali and alkaline earth metal, they always lose all of the maximum. Transition metal has opposite, to lose 3 or 6 or so on. Okay. Now, valence electrons for non-metal also corresponds to the Roman numeral on top of the column. But with metals, whatever the valence electron is what it can lose, right? That's not the case with non-metals, okay? For instance, let's choose nitrogen. I've already demonstrated that in the previous video. Nitrogen is 5A. phi b, sorry. What this means is, yes, nitrogen has 5 valence electrons, but non-metals don't use the 5 to bond. It has to gain what is lost by the metal it's pairing with, okay? And it will usually pair with the metal in such a way that it'll get the 3, okay? So what that means is, you have to take the 8 minus the 5b, means just worry about the 5, which means 3. What this is very, very important, okay? While metals lose valence electrons to bond, whatever it's losing is what gained by the non-metal it's pairing up with, okay? Non-metals, for instance, nitrogen, oxygen, etc. So oxygen is 6b. This doesn't mean oxygen will use 6 electrons to bond. Yes, it's got 6 already, but it will need 2 more, that is 8 minus 6 is 2. So that's how many valence electron it would need from the element it's pairing up with, okay? We're going to learn that in great detail in the next video when we learn actually writing formulas for ionic compounds, all right? So here's the newer topic. First, let's understand what is a bond, okay? There are 3 types of bonds: single, double, and triple, okay? All compounds contain a single bond, okay? Single bonds in chemistry is also referred to as sigma. In a double bond, you have 1 sigma and 1 pi. And in a triple bond, you have 1 sigma and 2 pi bonds, okay? So you can see the common recurring theme is all compounds, irrespective of what the compound is, they all contain a sigma bond, but whether they contain a pi bond or not is different, all right? So this is very, very important. So the point is, a bond requires 2 electrons. That is, to make a bond, it's like a bridge. You need 2 endpoints to connect to make a bridge. A bridge cannot be like this. That's more like a cantilever, you know? There's no end to it. Of course, you can make the bridge that way if you're rigid enough to hold it like this, but again, those are exceptions. So this is a bond. There's a sigma bond, and then you also need 2 electrons for a pi bond. So whether it's a sigma or pi, a bond is a bond, and a bond requires 2 electrons. There are 4 major types of bonding, but we're only going to focus on 3 of them, and that would be ionic, nonpolar covalent, and polar covalent. Well, ionic, we're going to go into in-depth. Nonpolar covalent and polar covalent, we're going to use a Linus-Pauling electronegativity table to address the concept, because we're going to come back to this again when we learn VSEPR model in the near future. All right, so stay tuned for videos on ionic, nonpolar covalent, and